Okay, this is the third part of ANOVA lecture. Okay, I'm going to show you an example and show you how to actually calculate F value and how to finish ANOVA. So here is a swimming frequencies example. Suppose we want to know why there are differences in the annual swimming frequencies exist between three regions of a metropolitan area: the central city, suburban region, and a rural region. We interviewed 8 individuals in each region and collected the following data. Okay, so now we actually have 3 samples, right? So we have sample 1 for central city, sample 2 for suburbs, sample 3 for rural. And in each sample, there are 8 observations. Okay, so they are all listed here in this table. And we also have sample size, right? 8, 8, 8. Sample mean and sample standard deviation, and eventually the overall mean and overall standard deviation for all 3 samples. They have been prepared. They are all here. So what you need to do is calculate F value and find out F critical value and compare them. So step 1 is always set up a null hypothesis, right? So here the null hypothesis is mu suburb is equal to mu central city is equal to mu rural. The alternative hypothesis is that 3 of them, they're not equal. Step 3, choose the significance level, right? So alpha. So alpha is equal to 0.05. Okay, usually this value should be provided in your question, and if not, if you're doing an actual research, you have to decide it yourself. Okay, and choose a statistical test and find the observed test statistic. So here, because there are 3 samples, right? So we're going to use F-test, which means we're actually carrying out an ANOVA test. And the test statistic is F, right? So in order to calculate F, we have to calculate BSS and WSS. I've finished them. I will just show you the processes here. I'm not going to address them step by step, okay? So BSS formula, WSS formula, you can find them in former slides. And I just just insert all those values from the tables provided uh, from the table provided before. Okay, so we have BSS result as 1,602 point something, and WSS 4,802 something. So TSS is the sum of WSS and BSS. You can just calculate them here. And eventually, we need to calculate F-test. And F-test is actually has nothing to do with TSS, right? So you just need to know BSS, you need to know WSS, you have to calculate the degrees of freedom for BSS and WSS. So the degree of freedom for BSS is 3 minus 1, K minus 1, which is 2. And the degree of freedom for WSS is N minus K, which is 24 minus 3 is what? Is 21. Then you just follow this formula. You should be okay to calculate, to find out a final value for F-test. Here, for this specific question, the value is 3.5. So you may see this process, I think it's straightforward. It's very straightforward. But if you want to make it more, say, organized, you can use a table to do that. I will show you later. Okay, so after you have the test value, you need to use table A5 to find the critical value, right? So F alpha K minus 1, N minus K. So alpha here is 0.05, right? K minus 1 is 2. N minus K is 21. You go to that table to the page for alpha equals to for alpha equals 0.05 and find out the critical value is 3.47. And then you compare your test value with your critical value, right? Because your test value is a little bit larger than your critical value. So we need to reject the null hypothesis, which means that the population means for central city, suburban areas, and rural, they are not the same. They are not equal to each other because we reject null hypothesis. Okay, so here is the table I mentioned before to make your calculation process more clear, more organized. So here, each row is for a specific quantification. First row is for between groups, BSS. Second row is for WSS. Third row is for TSS, right? So here you can just say that for the first column, that's just the name, right? For the second column, you can replace BSS with the specific value you have for BSS. You can do the similar thing for WSS and TSS, right? The third column is for degrees of freedom. So for BSS, it is K minus 1. For WSS, it's N minus K. For TSS, it's N minus 1. Again, you can replace these formulas with your specific values. And since you have BSS, you have K minus 1, you calculate the ratio, you have the mean square. BSS divided by K minus 1. That's actually the numerator for F-test. You do the same thing for WSS, right? You have the denominator. And then next step, you calculate the ratio between mean squares and you have F-tests, right? And a TSS, you can also calculate it, and eventually you go to F table to find out the critical value, right? So F alpha, K minus 1, N minus K. And the last step of ANOVA, you compare this critical value with the F-test value you just got from this table, right? So this table is actually very interesting because it is revealing the relationship between different parameters, right? For example, when you have BSS, you have the ratio between BSS and K minus 1. And you also know the value of F-test. According to the relationship between mean square between groups and mean square within groups, you can calculate the ratio between WSS and N minus K because you have the F-test value. And if you know the numerator, you can calculate the denominator. Okay, so in your homework, there will be questions about this, right? Some parts of this table has been provided. You need to use them as, say, clues, and you need to use the relationship between these parameters to calculate unknown parameters. Okay, so when you go to your homework, you will say what I'm talking about. So here, I replaced all those names and formulas with the actual values we got from that swimming example, right? So BSS, WSS, degree of freedom for BSS, degree of freedom for WSS, and you just calculate, right? Right. So F-test, and again, this is a critical value from the table. Okay, so eventually you will have the same result, right? So F-test is a little bit larger than F-critical. So what? So we reject null hypothesis. Next, in the last part of this lecture, I want to talk about the robustness to assumptions. Robustness of who? Of ANOVA to assumptions, because there are three assumptions you need to accept before carrying out ANOVA. But in real application, those assumptions, they're pretty hard to meet. Okay, so if, for example, my samples, they are not meeting one of those assumptions, partially not meeting, okay, of those assumptions, is the result of ANOVA sensitive to this deviation from assumptions? So let's talk about that. So firstly, normality. ANOVA is relatively robust to departures from normality, which means that even your populations are not strictly following normal distribution. It's okay. ANOVA is not very sensitive to that, which means it's relatively robust to departures from normality. And non-normality leads to slightly conservative results. What does it mean? It means that if your populations are not strictly following normal distribution, it's less likely to have type 1 error. Type 1 error means rejecting a true null hypothesis. And the probability of having type 1 error is alpha. So type 1 errors are less likely to happen than alpha, means that if your populations are not strictly following normal distribution, as a result of your ANOVA, you tend not to reject null hypothesis, okay? You tend not to make a type 1 error. So that's the result. So for the second assumption, this word is pretty hard to read, is called homoscedasticity or eco-population variances. This is the second assumption. So ANOVA is relatively robust, again, just like normality. ANOVA is relatively robust to departures from eco-population variances to this assumption. It means that, okay, it's all right if your actual population variances, they are not very equal to each other. It's okay. ANOVA result is not very sensitive to that. And heterogeneity. Heterogeneity is the other side of homoscedasticity, which means homogeneity means not equal population variances. It leads to slightly liberal results, which means you're going to be more likely to make type 1 error, which means you tend to reject the null hypothesis. It's not a very good thing because eventually it's an error, but this tendency is not that strong. So it means that, okay, ANOVA's result is not very sensitive to the departures from the assumption of equal population variances. So normality and equal population variances, they are assumptions, but ANOVA results, they are not very sensitive to these two assumptions. But the third assumption, independence, ANOVA result is very sensitive to departures from independence, which means that in order to get an accurate result from ANOVA, you have to make sure that when you are collecting observations for each sample, you need to make sure that all those observations, they are independent from each other, which means the value of one observation has nothing to do with the value of another observation. This is very common in geographic data sets because there is something called spatial dependence. It means that closer things, they are more likely to be similar to each other than remote things. Okay, so if there is spatial dependence, you want to make sure that all those observations in your sample, they are effective, which means they should be independent from each other. If some of those observations, you know that they are affected by others, they're not independent from other observations, you should delete them to make sure that all observations included in ANOVA test, they are independent, okay? Okay, due to the spatial dependence or any dependence, rejection of the null hypothesis may be due to this dependence or spatial dependence. Okay, so what is spatial dependence? Let me give you an example. For example, you're trying to survey the housing market of a specific city, right? And after the survey, you find out that, okay, most communities in this city, they have relatively similar housing price, similar mean housing price, see that. But there are several, say 2 or 3 communities, they have dramatically higher housing price than other communities. And you find out that this, this special high price, this abnormal high price of the 3 communities, they are due to a very beautiful lake located in that area containing these 3 communities. So here is spatial dependence. All those houses, they are expensive because of another factor, which is that beautiful lake. Okay, so in this case, if you are collecting observations, in this specific case, you are collecting house prices from these 3 communities, you need to be careful because there is spatial dependence. You want to make sure that you are collecting less examples. You are collecting less observations from the 3 communities than other communities because like I said, some of these observations, they are not effective. They are affected by the third party. Okay, so this is independence. So ANOVA is very sensitive to this. Okay, so when you are trying to carry out ANOVA analysis, normality of your populations is okay. Equal population variances, this assumption is also okay if it is not very strictly followed. But independence, data independence, observation independence is pretty important. You have to make sure that within each sample, all those observations, they were independently collected from each other. Okay, and between samples, all those samples, they should be collected independently from other samples. Okay, okay, so that's all I want to say about ANOVA. Okay, please follow the updated schedule to start and finish your homework, and also please remember to finish labs. Okay, for more details about the arrangement of labs, you can find them in the announcement I made 2 days ago. Okay, thank you very much.